Yeah, so thank you for having me. Really excited to be here. And as Annie said, I'll be talking about symmetry adaptogram spectrahedrons today. But to start, I'll just be going over, so this first portion, I'll be going over sums of squares, just sort of the basic theory of them, and also talk a little bit about symmetric polynomials as sums of squares. So that's where we'll start. And of course, if anything is unclear, please feel free to interrupt me. The way my screen is set up, I can't necessarily see a raised hand, so maybe someone else can actually interrupt me and then ask questions that come up. All right, so let me start with a little motivation. So here is a polynomial optimization problem, a POP. And we're taking the inf over all real numbers, right? So this is an unconstrained polynomial optimization problem even, of some polynomial p. So even this unconstrained polynomial optimization problem is in fact NP hard. So we'd want some ways to be able to address such problems with maybe somehow a little easier. So let me reformulate the problem a little bit. If you can think about it a little, it turns out this is the same as taking the soup over some number gamma, such that p is greater than or equal to gamma. And then of course you can just subtract the gamma over. And so now I've changed it slightly. It's an equivalent problem where we're now trying to certify non-negativity of a polynomial. Right, and still hard, but what we're going to do is relax this to a sums of squares problem, where rather than trying to show that p minus gamma is a polynomial, is a non-negative polynomial, I'm going to try to write it as a sum of polynomials squared. So what I mean by sums of squares here, I specifically mean a sum of polynomials squared. Now it is a relaxation, right? Not all non-negative polynomials are sums of squares. Of course, trivially, all sums of squares polynomials are non-negative, which is why it would certify that non-negativity. But now the next question is, well, why would we do this? Why is it easier? So that's what I'll talk about in a second, or now. So we're starting with a polynomial p, and I'm just going to make all my polynomials homogeneous. Meaning all the terms are the same degree, of degree 2d. Right? Has to be even degree if we want it to be a sum of squares. So a polynomial p is a sum of squares if and only if we can find a positive semi-definite matrix Q, something like this. That's what this notation here means, such that we can write p in this kind of quadratic form. And I'll explain the X bracket in a second, but if we could find a positive semi-definite matrix such that this equation holds, that's called a gram matrix. Now, and then that would of course certify SOS-ness of the polynomial p. The X bracket notation means it's a vector of all monomials of degree exactly d. So remember, we're starting with a homogeneous polynomial of degree 2d. Our monomial vector X bracket X is a vector of all monomials of degree d. All right, so what does this all tell us? It tells us that, oh, sorry, was there a question?
Yeah, maybe Isabelle, just for those who are not familiar with this, so this certifies that this is a sum of squares because Q then can be written as B transpose?
Yes, I actually have an example to illustrate that later. But yes, exactly. So the key to that statement is really the factorization of a positive semi-definite matrix. Exactly. Now, what does this does then is reduce the SOS problem to a semi-definite program, right? Where essentially we're searching over the positive semi-definite cone. So searching for a matrix Q that's positive semi-definite, intersected with some affine subspace defined in the coefficients of defined by the coefficients of the polynomial in the unknowns of our matrix Q. Right, so that's exactly a semi-definite program. You have this cone, the positive semi-definite cone, and you intersect that with an affine subspace. That gives you what's called a spectrahedron. In this case, the feasible region of the sums of squares program is called the gram spectrahedron. Right, and yeah, as Annie pointed out, not everybody here necessarily is familiar with this, so let's do a real simple example. I claim this problem is a sum of squares, or this polynomial, excuse me, is a sum of squares, and therefore non-negative. And what my little theorem above, or our little fact tells us, not a little fact, it's actually quite an important one, but what it tells us is if we want to certify sums that this is a sum of squares, is that we want to write our polynomial in this form, right? It's a degree 2 polynomial in 2 variables, so our monomial vector is going to be degree 1 monomials in 2 variables, so that's just x and y in this case. And so we have this cube, this 2 by 2 Q matrix that we need to search for in order for this equation to hold, and we need it to be positive semi-definite, right? That's the idea. Now, if we actually multiply this out, the top left corner corresponds to the x squared terms. That's going to have to be a 5. The bottom right corner is the y squared term, so that's going to have to be a 2. And then if we want it to be positive semi-definite, it has to be symmetric, so the anti-diagonal entries have to be equal, and they have to sum to the xy coefficient, so that's going to be -2, so those are going to be -1. And in fact, this is a positive semi-definite matrix, right? The principal minors, in this case, the 2 diagonal entries, and then the determinant itself are all non-negative. So it is, in fact, a positive semi-definite matrix. And so I have now certified for you that this polynomial is, in fact, a sum of squares, which maybe isn't satisfactory. I haven't actually written it as a sum of squares, right? So let's actually do that. And this will illustrate sort of what the key factor is in the proof of the statement earlier, which is that we can factor a positive semi-definite matrix into something of the form U transpose U. Pick your favorite factorization. I chose one here. And if we multiply this piece out and then this piece out, and then actually take the dot product, we get that this polynomial is -2x plus y squared plus x plus y squared. Let me point out one thing which will come up a couple of times. This is a rank 2 matrix, which is exactly why we end up with 2 squares in our decomposition. So the rank of the matrix that you find, your gram matrix, corresponds exactly to the number of squares in your sums of squares decomposition. So that's a quick intro to sums of squares. I'm going to move on to symmetric polynomials in a second, but let me pause here for any questions.
Could you repeat the thing about the rank?
Yeah, of course. So in this example, there was one matrix that was our gram matrix, right? But there are possibly many gram matrix representations for various polynomials, and the rank of that matrix, if it's rank 5, that means that your sums of squares decomposition will have 5 squares in it. So the rank is exactly the number of squares in your sums of squares decomposition. Cool. Okay, well, let me move on to symmetric polynomials. So there's some representation theory working in the background here that I don't really want to go into really for the whole talk, but there's going to be some in the background, so just be aware of that. We're going to start. So I have a symmetric polynomial, and it's homogeneous and degree 2D. By symmetric, I mean just a sort of normal invariant under permutations of the indices of the variables. But what I'm interested in is Sn acting on the space of degree D polynomials, right? So we started with a degree 2D polynomial, but I'm going to consider the action of Sn acting on the space of degree D polynomials. So kind of think of that monomial vector we had earlier. This has a matrix representation. I'm going to assume it's orthogonal. In fact, with Sn, everything works out nicely with the monomial basis. But yeah, I'm going to assume my matrix representation is orthogonal. Then that induces an action on the space of symmetric matrices. So you can see in here, you can have an action on the space of symmetric matrices X by conjugation. And I'm interested in the space of symmetric matrices that are fixed by that action. So what we call the fixed point subspace. Now, why am I interested in that? It turns out that if you have an invariant semi-definite program, then you can optimize over, rather than looking at the entire PSD cone, you can actually restrict to the fixed point subspace. And for symmetric polynomials, for the sums of squares problem that arises from symmetric polynomials, that is in fact an invariant SDP. So rather than searching over the entire PSD cone, I'm going to restrict to this fixed point subspace. And this allows us to do one of two reductions to the problem size, right? So the goal here for symmetric polynomials is to exploit the symmetry to make the problem a little, the sums of squares problem easier somehow. And this theorem allows us to do that. So let's go through a very small toy example. I know everyone here can factor this and see that it's a sum of one square, but let's just pretend we can't. It's a degree 4 symmetric polynomial in two variables, and I claim, without knowing how to factor, that this is a sum of squares. Well, what's our representation here? We have S2 acting on degree 2 polynomials in two variables. And we're going to think about it in the span of the monomial basis. So that's x1 squared, x1, x2, and x2 squared. And in this ordering. In this ordering, we have a matrix representation where, of course, the identity element is just the identity matrix. And then the permuting by 1 and 2, that element has this matrix here with 1s on the anti-diagonal. And with Sn being just the nicest group possible, that means that the fixed point subspace is exactly the set of symmetric matrices that commute with this representation. So really it's just, of course, everything commutes with the identities. So it's really just, we restrict to matrices that commute with this matrix here. So let's see how that plays out in this example. So if I wanted to write this as a sum of squares, the earlier theory that we had tells us that we would write our polynomial P in this form, right? We need to find some 3 by 3 Q matrix that's positive semi-definite such that this equation holds. Here's my monomial vector of all degree 2 polynomials in two variables. It's a symmetric, it's a symmetric matrix, so there's 6 variables, but if we restrict to the fixed point subspace, right? So if we have it commute with that representation, matrix representation I showed a minute ago, we find that Q11 and Q33 are the same, have to be the same, have to be equal, and Q12 and Q23 are equal. So we've now reduced the problem size from a degree, from a 6-dimensional problem to a 4-dimensional problem. We reduced the number of variables and indeterminants by 4 already. So that's nice. That's the first reduction that we can do in terms of actually finding and solving this this problem, this SOS problem. The next one's a little more complicated, and I will actually talk about it in the second half of this presentation. I just wanted to present it here so that everyone's kind of seen it at least once, and then can digest it for 10 minutes, and then we'll come back and talk about it again. But representation theory tells us that we can block diagonalize our matrix D, our matrix representation D sigma. You can calculate this matrix, this change of basis matrix T. You can calculate it so that it's orthogonal, in fact. And it turns out that it also block diagonalizes our Q matrix. Right, this is after, of course, this is after we've actually restricted to the fixed point subspace. So we're block diagonalizing this matrix here. Now, I'll speak a little bit more about this later, but how would we actually use this block diagonalized version? Well, here's our equation, right? We have P, and we want it to be equal to something over here, to this equation, this thing on the right. And I calculated my change of basis matrix T to be orthogonal. So I can plug it in like this, because these are just the identity. And then we kind of manipulate things around. And so now you can see in here, we have our block diagonalized matrix. And over here, we have T transpose times our X bracket vector, right? And same thing over here. And so what we're really doing is changing the basis of our space of degree D polynomials, right? We started with the monomial basis, but I'm going to change it to what's called a symmetry adapted basis. And I do this because now I have a block diagonalized structure in the middle. And this matrix here is positive semi-definite if and only if Q is positive semi-definite, right? So this is the next sort of simplification to the problem. We can now, instead of trying to make Q positive semi-definite, we can make this matrix positive semi-definite, this block diagonalized version, and that's positive semi-definite if and only if each of the blocks is positive semi-definite. So we kind of break it up into these smaller problems instead. So let's do that with our example. We can calculate T, there's algorithms for it, and in fact, this is what our Q matrix ends up looking like. So we get these two smaller cases, or excuse me, two smaller blocks. I'm not going to go through and solve this problem, but if you wanted to do so, maybe on the 10-minute break, or if you get bored of my talk later, you can expand this out, right? This top equation out to get the affine subspace in terms of the coefficients of P. Then once you have that, plug that in here and see if you can find what the positive semi-definite matrix would be. There is in fact only one solution, and it's exactly what you get when you factor this, which would mean it's a rank 1 matrix, right? So if you do it right, you should get a rank 1 matrix at the end. Yeah, and that's all I have for this first portion. Are there any questions?
Well, first, thank you, Isabelle. So we do actually have quite a few people who care about representation theory here. So can you just say something quickly about the number of blocks you get?
Yeah, I will actually
will
in the second half of the talk. Yeah, so that there'll be some repeated slides and then more information about that. But I mean, I guess, should I do it now, or do you want a surprise later?
As you wish. Yeah, good.
Yeah, like so I'll kind of actually go over it later, but I'll maybe show you now. So right, so you get these blocks here are actually, they correspond to the Europes of Sn. And inside the blocks, inside of these Qi tildes, we have multiple copies of another smaller block. And the number of copies, as you can see written here, the number of copies is actually equal to the dimension of the Europe that's associated to Q tilde I. And in fact, the size of the Qi is equal to the multiplicity of the Europe, which is pretty cool, I think. Yeah. Oh.
More questions?
So I have a question. So could you start with like some known symmetric functions, like a Schur function, or yeah, just
Yeah, absolutely. I mean, so certainly you can give me any symmetric polynomial, and then I can do the theory for this and write it or determine whether or not it's a sum of squares, right? Doing this certification process. I personally, I'm not sure how to do that, and you would have to give me like the specific polynomial. So one difficulty we had with looking at actually specifically symmetric polynomial inequalities is that a lot of these statements are claims for where the polynomial has any number of variables, right? And in fact, this sums of squares machinery, you really have to know the number of, you have to kind of know the polynomial, really. So you can't kind of generalize, at least I haven't been able to figure out how to generalize it to sort of, all Schur function inequalities are sums of squares kind of thing. There's some work that Cordy and Rayner and Greg Bleckerman have done where they like nest symmetric polynomial, or excuse me, they nest they take symmetric polynomials of a particular number of variables and degrees, and then they map them to the next version of that polynomial by adding a variable and then symmetrizing. And then they kind of like do this nesting process of symmetric polynomials and prove some really, really interesting things with sums of squares of symmetric polynomials. But that's like in like the limit of the number of variables. But yeah, I've only seen that done with what they did, which is specifically power sum symmetric polynomials.
Thank you.
Can I ask you something? Talking about, can you hear me? Sorry.
I can hear you.
Talking about inequalities, can you do the majorization inequalities as sums of squares? This might be known, I'm not sure.
Majorization inequalities? I don't know what that is.
Oh yeah, so the majorization inequalities are when you have a symmetric polynomial that is, the powers of the monomials are more isolated, so like x to the third plus y to the third plus z to the third, that would be bigger than a symmetric polynomial where they're more spread evenly, like x squared y plus xy squared plus etc. So you would start with two partitions, one majorizes the other.
Oh, sorry. Yeah. I think I know it as dominance ordering, which is the same thing. Yeah, yes. So yes, and actually we did do this for, and I'll talk about this actually later again in the presentation. We did this for, there was a theorem for term normalized homogeneous symmetric polynomials, or actually there was a conjecture suggesting that these inequalities would hold given partition dominance order. And again, I'll talk about it later as an application of this. And we actually found a counterexample to that conjecture using sums of squares. But again, it's sort of this difficulty of, I'm not sure how to generalize it to general statements using the sums of squares machinery, because everything changes. You know, the gram matrix, the PSD cone that you're looking at will change depending on the number of variables and the degree that you have. Yeah, so I think there should be something for that, but that is yet properly unresearched territory, I think.
Oh, it sounds cool.
Any more questions? Okay, all right, so let's take a short 5-6 minute break. We can hang out and talk. I'll go get something to drink.
Yeah, I'm gonna get some water and then I will be right back. Can you guys hear me okay now?
Yeah.
Okay, good. I muted my other mic and not on Zoom. So.
How's everybody's electricity in the Northeast? Everybody okay?
I didn't have any issue. It went on and off on the other night, but it was like not even a minute.
Alejandro didn't have any for 30 hours.
Yeah, it was
Yeah,
about.
there are places where they were expecting until like Saturday.
Oh.
I didn't even know there was a problem. We didn't have any issue.
What caused it?
Wind.
Windstorm. And so a lot of trees fell down.
Yeah, there are a lot of trees down.
Yeah, some people don't have internet either. So some people have electricity and no internet. Then some people have. Yeah.
I guess I don't see very many overground power lines where I am. Maybe they're undergrounded around here. I don't know.
Maybe
It
your
seems like
neighborhood
a
is more recent.
It's a newer neighborhood, right? It's only the
Hmm.
house is less than 20 years old, so maybe that's part of it.
Yeah, I had a student who was supposed to take an exam that evening, and like a huge tree fell into his backyard and took down the power line. And he was like, my internet is like he could use his phone, but not his computer. And I was like, that's fine.
Wow.
My internet was also going in and out, so it was better.
Yeah, the storm was only for like what 5 to 6 minutes or something, and it seemed like it did a lot of damage. Our car was damaged by a storm a month ago. This was in New York. A tree branch fell on top of my partner's car, and we had to tow it. And we got a new car recently, and that car was parked outside. So the 4 to 5 minutes during the storm, I was staring outside the window like this, thinking, should I run out of the storm and repark the car or not? They don't want my partner to come back home to another damaged car. But no, it ended before the...
Like it damaged it so much that you had to tow it, okay?
Yeah,
Like-
it cracked. Like I have a picture somewhere, but it cracked. It wasn't like... The people said it can go either way, the insurance people. We've seen worse. One of his colleagues, entire tree fell on his car, and that one definitely had to get towed. But I'm not sure if you guys can see it, but...
Oh yeah, the back windshield was completely gone.
Yeah, the back windshield is completely gone, and the car itself is a little bit crushed. If you like zoom in, so then like... yeah, but apparently towing is easier because we get some money from the insurance as well. And we were able to get some good deals from the, there was 0% APR deal at the car company. So we're like, okay, all right, well, we'll go for this.
So I was
What
gonna.
fell on it?
Oh, yeah, go ahead.
Sorry, what fell on it?
Oh, a tree branch, like a big one, really heavy one. Yeah.
I once saw an icicle fall into a car windshield. That was interesting because it was happening as I was walking up the hill.
That is terrifying.
No one was in the car. I mean, it was a parked car. But yes, it was. I mean, I grew up in upstate New York. There's signs that go up everywhere on campus being like, watch out for falling ice and snow. I think in my first year, like, snow fell off of one of the roofs of the building and like 3 people got concussions. Like, they can't really do anything except climb on the buildings and create avalanches. So, and Colgate wasn't about to do that. So yeah, it's horrible, but like 2 hours away, people would die on the highways because trees would fall over. So like,
Perspective.
I was gonna say that cars right now just get like super compressed because they are supposed to take all the damage. So they're supposed to be more secure. Like years ago, your car will be not like, you will not see anything happening to the car, which is actually not more secure if something really bad happens and then you have metal. So now the cars will just like get super destroyed, but if you are inside, it's good.
I didn't know that, but yeah, our tenant also had a tree branch fall on her car about a month ago, and I was impressed. Like somebody came to fix her car, so they changed the windshield, and there was like a huge bump into on her hood, and it just took like the big suction cup.
Really?
And lifted it up, and like it took a second, and I had never seen that being used. It was impressive.
Taking all the impact in the car. So that's really cool.
Yeah, no, I was impressed. All right, we are at 3:01, so maybe let's get started again. So again, it's our pleasure to have Isabelle, who will now tell us a bit more deeply about symmetry adapted ground spectrahedra.
Yep, that's the plan. So thank you again. So to start, this is joint work with Alexander Heaton at the Max Planck Institute in Circus Houston at San Francisco State University. And so I'll reiterate a bit about symmetric polynomials as sums of squares, and also talk a little bit more about it. So some of my slides are repeats. So for those of you who were here for the first half, please bear with me. And then I'll go into the properties of what I call the symmetry adapted PSD cone. then talk about symmetry adapted gram spectrahedra for particular cases of N and D that we studied, N being the number of variables, D being the degree. And then I'll end with some of the work that we did applying this machinery to symmetric polynomial inequalities. So I kind of touched on that earlier, and I'll actually, go into it a little bit more in detail here today. Right, so again, we start with a polynomial of degree 2D, and we have, we consider an action of Sn on the space of degree D, polynomials, and N variables. This has a matrix representation, which I again assume is orthogonal. And I'm interested in the fixed point subspace of the action induced by this by conjugation on symmetric matrices, right? So we have this D sigma action, and it acts on the space of symmetric matrices by conjugation. So the fixed point subspace, it turns out, is, as I said earlier, all we really need to look at when it comes to looking at symmetric polynomials as sums of squares. So that's according to Gutterman and Perillo, this theorem that I referred to earlier. And like I said, the big thing here is really just that rather than looking over all symmetric matrices or the entire PSD cone, we can restrict to a linear subspace actually of the PSD cone. I had this example earlier of a degree 4 polynomial in 2 variables. This is symmetric. And if we want this matrix to commute or to be fixed under the action induced by the matrix representation D sigma, then we get that Q11 and Q33 are equal, and Q12 and Q23 are equal. So again, we go from a 6-dimensional space to a 4-dimensional space. We can also consider what we call a symmetry adapted basis. So rather than looking at the monomial basis or some other basis, we'll specifically choose a basis of the space of degree D polynomials and N variables such that we can take advantage of certain properties. So in particular, I'll calculate the change of basis matrix T that does this. Specifically, I'll choose it to be, or I'll calculate it to be orthogonal. I can do that. This change of basis matrix block diagonalizes our matrix representation D sigma, and as I said earlier, it turns out it also block diagonalizes our Q matrix after we've done that initial reduction in the number of indeterminates of our Q. Now, I won't go too much into the rep theory, but and I think again I said this sort of after the questions, but I'll just reiterate. Sn. So we have an Sn action on the space of degree D polynomials. That vector space decomposes into irreducibles of Sn, and that informs the structure, that decomposition informs the structure of this matrix. In particular, each Qi tilde is associated to one of those irreps, every irrep that appears. So every irrep that has, excuse me, by irrep I mean irreducible representation. So I'll say sometimes I'll just say irrep. But yeah, so each Qi tilde corresponds to a particular irrep with multiplicity greater than 0. And these Qi tildes have these copies of blocks Qi's in here that are all identical. And the number of copies is in fact the dimension of the corresponding irrep. Not only that, but the size of these Qi's in here is equal to the multiplicity of the corresponding irrep. Right, so let's say for the standard irrep, where we know that's going to be n-1 dimensional, so there are going to be n-1 copies of matrices in there, and then whatever the multiplicity might be, let's say it's 3, that means that these matrices in here are going to be 3 by 3 symmetric matrices. So that's really nice. We get this information about the structure of this just from the decomposition into irreducibles of our space of polynomials. And again, why would we do this? The first step that we talked about, the first thing with the theorem, with the Perillo-Gutterman theorem, was that we actually reduce the number of variables. So that feels kind of obvious, like why we would want to do that. It certainly reduces the space of the problem, the size of the problem. Here, block diagonalizing, what it allows us to do is look at these individual blocks, right? So it's positive semi-definite if and only if the blocks are positive semi-definite. So that's the next kind of reduction to problem size that we do in the case of symmetric polynomials. I should say that all this theory actually extends to all invariant polynomials that are invariant under a finite group action G for finite groups really nicely. And actually, if I understand correctly, and I think, so my representation theory is actually quite weak, but if I understand correctly, it actually extends to all reducible groups, I want to say, but certainly the finite ones, right? So this theorem by Perillo, Gutterman, and Perillo was just for finite groups, but I think it actually extends to more than just finite groups, some particular nice groups. And so we'll see the block diagonalization here again. Once I've reduced the number of variables from 6 to 4 in this example, we can calculate this change of basis matrix T to block diagonalize our matrix Q to this. And if anybody actually took the time to solve it, you should have gotten, I believe, a 0, but a bunch of zeros up here and like a 2 down here. So that when you factored it, you would have gotten just, excuse me, yeah, when you factored the matrix, you would have gotten just this factored back. Right, so this this cone, right, so this is actually, I mean, what have we done? We've taken the PSD cone, we've intersected it with a linear subspace, and then we've block diagonalized it, so just done sort of a change of basis, right? So this is actually a cone in and of itself, and this is now the cone that we're optimizing over rather than the bigger PSD cone. So Sirkin and Alex and I were interested in studying this cone, like what are its geometric properties, and the first sort of, what we call it is the symmetry adapted PSD cone. So the first sort of question was, well, what's the dimension? And you can see it here. We found that it was, if you let m lambda I be the multiplicity of the irrep labeled by lambda I, then it's exactly summing up the m lambda I plus 1 choose 2 overall irreps that appear. And here just m lambda plus 1 choose 2, it's basically the number of free parameters you possibly could have had in one of those QI blocks, right? Because these are symmetric matrices, so it's the most number, or the greatest, it's an upper bound for what the dimension could have been, and in fact that is what the dimension of the cone ends up being. So it sort of hits the upper bound that you would expect. The next question oh, sorry, go ahead.
Sorry, one question. So for the previous example, the m's would be all 1, since in these 2 blocks?
Actually, the multiplicity, so this block is associated to the trivial irrep. That's why there's only 1 copy, because it's 1-dimensional, but the size is 2 by 2. So there's actually multiplicity 2 in there. So there's 2 copies of the trivial and 1 copy of the alternating in this decomposition. Yeah, good question. Other questions? Cool, so then the next question we asked was about extremal rays. And so for some context, the PSD cone, you take a matrix in the PSD cone that is rank 1, then all the scalings of that extremal ray, that ray, excuse me, is an extremal ray of the PSD cone, and all extremal rays in the PSD cone are found this way. They're all defined by rank 1 matrices. So what about the symmetry adapted PSD cone? Well, it turns out that the way to construct an extremal ray is take one of your QI tildes, one of these blocks, and make all the other ones 0. Then you have in this QI tilde, maybe I'll even go back. So pick one of these QI tildes. In one of these QI tildes, you have multiple copies of the same block, right? So you're going to make you make QI rank 1, but then the rank of QI tilde is exactly the dimension of the irrep, right? And that matrix now defines an extremal ray. So what we found, in fact, is that the extremal rays of the symmetry adapted PSD cone are in bijection with the dimensions or the rank, excuse me, the matrices defined in this way. I guess that's the best way to say that. Meaning that the ranks of those matrices that define the extremal rays are actually going to be exactly the dimensions of the irreps that appear in your decomposition. In the SN case, you always get the trivial representation, so you'll always get rank 1 matrices, but there are actually other interesting cases. So in our paper, we look at the icosahedron and find that the irreps that appear there are dimension 3, 4, and 5, which means that the extremal rays of the associated symmetry adapted PSD cone will all be defined by matrices of rank 3, 4, and 5 exactly. So it's kind of a neat little difference, I think. Okay, so we have this cone, right? So in maybe, let me take a second to step back. So in the sums of squares problem, we had this big PSD cone and we intersected it with the affine subspace defined by the coefficients, right? Now we were looking at a smaller piece of that cone, the symmetry adapted PSD cone, but then, you know, we're interested in a particular polynomial, then we're gonna again intersect that with some affine subspace defined by the coefficients of that polynomial. And that's what we call the symmetry adapted gram spectrahedra. It is in fact a piece of the larger gram spectrahedra, but according to the Gutterman-Perula theorem, it's all we have to look at if we're interested in finding a sums of squares decomposition, even one where maybe you're trying to maximize or minimize something, right? So what are the properties of those symmetry adapted gram spectrahedra? Well, we have to look at particular N and D in this case, so that's something I was talking about earlier. And so that's what we did. We looked at particular cases of number of variables and degree. And I'm just going to go through a few of the ones that we talked about in the paper. So let's start with symmetric quadratic polynomials, so degree 2 polynomials in any number of variables n. The symmetry adapted PSD cone turns out to be this diagonal matrix, even not block diagonalized, but it's in fact a diagonal matrix. So we get this 2-dimensional space. Here we have a 1-by-1 block for the trivial, and here we have n-1 copies for the standard irrep. And if this matrix is positive semi-definite, that's if and only if, that's true if and only if the diagonal entries are non-negative. So we just get this polyhedral cone. Right, this top line here, or this top ray is for the standard blocks, and then this bottom ray here is for the trivial block. What it turns out that every point in the plane actually corresponds to a unique polynomial, which is nice because then this actually gives us some sense of the volume of sums of squares symmetric quadratics, the ratio of sums of squares symmetric quadratics to all symmetric quadratics. In fact, the slope of this line as the number of variables goes to infinity starts to move up. And so we can see that in the limit, as we let the number of variables n go to infinity, the number of symmetric sums of squares quadratics, or the ratio, excuse me, of symmetric sums of squares quadratics to all symmetric quadratics is actually 1/8. So that's kind of a cute result. I'll move on to symmetric ternary quartic. So here we have polynomials with 3 variables, degree 4, which means our gram matrices are going to be 6 by 6. The symmetry adapted PSD cone looks like this. We have the trivial block and these 2 copies of the standard. The alternating in this case doesn't appear. And these are all 2 by 2 blocks. You can see them here. Now, if we're interested in the symmetry adapted gram spectrahedra, then we're going to want to pick a particular symmetric ternary quartic. So here I have one, let's fix A, B, C, and D, and I have it written here in the monomial basis. Then we intersect the affine subspace, or this affine subspace defined by those coefficients with the symmetry adapted PSD cone, and you get that the symmetry adapted gram spectrahedron is going to be the intersection of these 2 spectrahedron. Right? This matrix here comes from the trivial block, this matrix here comes from the standard block. And it becomes a two-dimensional object, so we can even see it. So this is actually quite nice. Generically, a positive symmetric ternary quartic will have this as its symmetry adaptogram spectrahedra. It will look like something like this, where we have this left component of a hyperbola coming from the standard block, and this parabola coming from the trivial block. So the intersection of these two spectrahedron, this region in here, is the symmetry adaptogram spectrahedra for a generic symmetric ternary quartic. And we can in fact completely describe the boundary of this. In particular, as I mentioned earlier, rank of matrices in the spectrahedra correspond to the number of squares in your sums of squares decomposition, right? So we're interested in understanding the rank along the boundary. For a typical, not necessarily symmetric, well, actually, I guess first the symmetric case as well, but for ternary quartics that are sums of squares or that are positive, the Gram spectrahedron has 8 rank 3 vertices, or they're called the vertices of the Gram spectrahedron, and only 2 of those 8 survive in the symmetry adapted case. So that's what these 2 vertices are. These correspond to the 2 invariant rank 3 matrices. Which will then give us a decomposition of 3 squares. Along the boundary of the parabola, we actually get rank 5. We get rank 5 matrices, and along the boundary of the hyperbola, we get rank 4 matrices. So we have kind of a complete understanding of the geometry and the structure of this. Now we wanted to do the same for symmetric ternary sextics. So here in the symmetric ternary sextic case, you see the PSD symmetry adapted PSD cone. Again, trivial copy, 2 copies for the standard, and now we do actually see the alternating up here. This restricting to the fixed point subspace reduces the dimension from 55 actually to 13. So you know, in these bigger cases, you see that the reduction size actually is quite significant as the problem grows, which is, you know, one of the big reasons for doing this, so that we can actually solve bigger problems, right? And then to get a better sense of what the boundary looked like, we ran some computations. So each one of these graphs corresponds to a random symmetric ternary sextic that is a sum of squares. So we ran random polynomials, and we picked out the ones that were sums of squares. And then for each of those, we ran random cost functions for those and ran the SDP for random cost functions 1,000 times to try to get a sense of what ranks we got. So these are the numbers down here correspond to the rank of the matrix for a given solution, and then the bar is how many times we got that solution. So you can see, like, somehow the normal fan of this convex object, the rank 6 portions should somehow dominate that. That's kind of what we get from this data, but we weren't really sure about what else we could say in terms of, I think some interesting things that we should, you know, think about are, you know, what are the vertices for this spectrahedron, and so on. Yeah, so that's what I have to say about the symmetry adaptogram spectrahedra, sort of the geometry and the real algebraic geometry behind it. I'm going to move on to symmetric polynomial inequalities next, but I'll maybe stop and see if there's any questions.
So sorry, I have a question. So in the example, the one you just did, the 10 by 10, so you take basically you have every representation appearing its
this one.
its degree, like so for example, you have 2 copies of Q21. So in S4 you would have all the, like, kind of the regular
So for S3 we did get that in this case we did get that in 3 variables. We got all 3 irreps appearing. But I think actually in general it's I might have to think about it again, but if I remember correctly, we did actually calculate that a lot of the irreps shouldn't appear.
Okay.
So like the alternating, I think eventually, if you have enough a high enough degree or high enough number of variables, I can't remember which one it is right now, the alternating should disappear entirely. So yeah, quite a few of the irreps actually don't necessarily make it. This might be one of the examples where it does, but yeah.
I guess in our setting, we had some result about just needing hooks as well.
Mm-hmm.
Do you have that appearing too?
Yeah, we had actually wanted that. So we looked at your paper to see if maybe there was some way we could restrict to certain types of partitions. But as far as we could see, there will always be, I think, cases where all of the partitions, all of the irreps appear. What we didn't, I think maybe I think a question about taking either the degree or the number of variables, probably the number of variables, taking that to the limit might cause you to have certain shapes only appear. But yeah, we haven't quite explored that as much as we should. We were hoping for some similar result actually, and we couldn't quite get it.
Can I follow up with Alejandro's question? Is any relation between the number of variables and the length of the partition? Because here you're considering partitions of 3, but some, like, you are going through the different lengths. So is the number of variables fixing the maximum length of the representations appearing?
Yes, I think so.
I'm thinking that in the PET-CSM, if you restrict to the number of variables, then you don't have partitions appearing that has more than that length.
Right.
So it's something similar happening here.
It might be. I would have to think about it a little bit more, but maybe. Okay. Yeah, that would be nice.
That would be cool.
Cool. Well, I think I'll continue with polynomial inequalities, symmetric polynomial inequalities. So let me start with some definitions. Given a symmetric polynomial G, I'm going to take that polynomial G, I'm going to evaluate it on the all ones vector, and then divide by that number. That new polynomial I call the term normalized symmetric polynomial of G, and I just denote it by capital G. So just as a simple example, here's the power sum symmetric polynomial for partition 3(1) in 2 variables. And if we actually evaluate this polynomial on the all ones vector, we get 2 times 2, so 4. And so the term normalized symmetric polynomial of this, which I denote by capital P, is just the same thing divided by 4, multiplied by 1/4. So this is the term normalized symmetric polynomials. And the notation I will use for the basis will again just be the capitalization. So by capital M lambda, I mean the term normalized symmetric polynomials for the monomial basis, E for elementary, P for power sum, H for homogeneous, and S for sure. Now, and I think this was mentioned earlier, but there's a paper by Cutler, Green, and Scandera that sort of collected all the information about symmetric polynomial inequalities, specifically talking about these term normalized symmetric polynomials, and when the inequalities hold based on partition dominance, what I call dominance order. Right, so I include SRA here because the statement for the Schur polynomial case was actually only proven in one direction, and the other direction was proven later by him. But yeah, so this is sort of multiple theorems all lumped together. But for example, we have here that the term normalized monomial symmetric polynomial with respect to lambda is less than or equal to m mu. So this inequality holds on the non-negative orthant. So to be clear, this notation here means that the inequality holds on the non-negative orthant if and only if mu dominates lambda in the normal dominance order for partitions, right? And we have similar statements for the elementary the elementary symmetric polynomials, the power sum, and the Schur symmetric polynomials. And we have one direction is true for the homogeneous, the complete homogeneous symmetric polynomials. That is, if partition dominance holds, so if we have mu dominates lambda, then this inequality will hold. We'll have h mu is greater than or equal to h lambda on the non-negative orthant. And Cutler, Green, and Scandera conjectured that the other direction held as well. That was in a 2011 paper. But when Curtis Green came and talked about this in a seminar actually a couple of years ago, he was pretty skeptical that this was true at that point. What they had said in the paper is that they had managed to prove it for partitions up to 7. And so they thought that if there was a counterexample, it would probably be in partitions of 8. And that is in fact what we decided to set out to do. We searched over incomparable pairs, so that's the strategy, right? We searched for incomparable pairs of partitions of 8 specifically, such that this inequality still held on the non-negative orthant. And we found that we actually found quite a few counterexamples, but one of them in particular that we then went and found a rational exact sums of squares decomposition for was for the partitions 4, 4, and 5, 2, 1. So these are in fact incomparable in dominance order, but h mu minus h lambda, or h 4, 4 minus h 5, 2, 1 is non-negative on the non-negative orthant. In fact, a sort of related polynomial is a sums of squares. So that is what we decided, this is how we decided to prove this statement. We took actually the polynomial for h44 minus h521, and we inserted squares into it. We took the 3-variable version, we inserted squares so that we wouldn't have to deal with this non-negative orthant condition. Unfortunately, that did mean that it increased the degree of the polynomial from 6 to 8, and so that made our gram matrix huge. We ended up with 45 by 45 matrices that we were searching over, which is why we ended up with a rank 41 matrix, and so a decomposition of this polynomial into 41 squares with rational coefficients, so that's kind of nice. But yeah, so this being a sum of squares certifies the non-negativity of this polynomial and therefore disproved the conjecture. Just so you have a taste of the matrix, here's the first row. We did this like rational rounding because, you know, well, maybe for those of you who don't actually know, the STP solvers all give back numerical solutions, and we wanted an exact solution to at least one of our counter examples. And so we did like rational rounding, and that's why you end up with these huge denominators in here. Yeah, and so the gram matrix is absurd, and I think that there are definitely probably better gram matrices. We would just need to actually find them. Now, if a numerical certification is good enough for you, then here, these blue arrows are in fact all counter examples that we found in partitions 8, 9, and 10, and only in 3 variables actually. You can see here is the 4, 4, 5, 2, 1 counter example. So each one of these arrows represents an h lambda minus h mu polynomial, and each arrow means that there was an SOS certification found for those pairs. We ran it over all pairs and not just incomparable pairs, so the black arrows are actually dominance order. It's the blue arrows that are the counter examples, so those are pairs of partitions that are incomparable in dominance order but still gave an SOS certification, a numerical one. We actually drew up these post sets hoping that we could maybe see some interesting pattern in here, but we couldn't. If maybe one of you can, I would love to hear a little bit more. If you see a pattern, that would be really, really cool. But yeah, so that was a nice application, I think, of the sums of squares for symmetric polynomials machinery. And I will end there. Apologies for running a little late, but thank you.
Thank you, Isabelle. Yeah. Yeah, I was hoping you were going to say, oh, we have a new conjecture, which from some patterns that we've observed. But, all right.
Not quite. I am hoping actually that, we stuck to 3 variables, right? And I honestly think that because the homogeneous symmetric polynomials behave like the elementary symmetric polynomials, when you take like the number of variables to go to the limit, I think the conjecture might actually be true in the limit of letting the number of variables go to infinity. And so that's something I'm really interested in actually exploring next. Yeah, so maybe some version, because it's a little unfortunate somehow that like all these other if and only if statements hold for all of the bases and then this one just doesn't. But maybe like some version of it does. I think that would be really cool.
Is it too early to ask like what kind of pattern you were hoping to get from that and what you could have said from it?
I mean, I think at this point, I think we were hoping to find like a poset of SOS-ness. That was like what we wanted, some kind of a pattern, but there was no real insight or like intuition into what that pattern might be. Yeah.
So you showed us like that the ratio of SOS symmetric quadratics over symmetric quadratics was 1/8, right? And so Kalyan and Greg have this conjecture about if you look at SOS symmetric functions over just symmetric non-negative norms, right? And they think that in the limit, they're the same. Have you looked at that conjecture at all?
I haven't,
Okay.
but I should, and that sounds very interesting.
Yeah, so like as a number of variables, goes to infinity, then somehow the SOS symmetric subsquares can represent all non-negative forms.
Oh, yes. Okay, I see. Yeah, they've done this. They've proven it for degree 4 polynomials.
Yeah,
That's right. Yeah, and then the conjecture is So I believe Cordian's student is working on degree 6 right now, is my understanding. But yeah, I think I think I think it's a really interesting result because they like I said, they took this like limit in specifically looking at power sum inequalities or power sum symmetric polynomials, and I wonder like if you could do something similar with others. And that's actually the direction I want to go for the homogeneous polynomials, to see if maybe we can prove the conjecture in the limit for homogeneous polynomials, to see if we can like do these nested things with that. But yeah, that's a project I have not yet started.
So I have a question for the cases when it's known. Is it possible to give like SOS proofs of the positive results of the, let's say, for the elementaries or for the shores?
Yeah, I mean, I think right. So all of this machinery works for any of the inequalities. As a proof for the inequality for any number of variables, it's again this issue of the Graham spectrahedra being specific to the number of variables and the degrees. But I wonder then if using this limiting technique that Greg and Cordian did might actually solve that. And I think that was their motivation, was looking at power sum inequalities actually. So there's some hope there, I think, in that direction, and that's the only direction I really know where there might be some hope of doing that for any number of variables, basically.
More questions for Isabelle? All right, well, let's thank Isabelle again.